If Peter Pan in fairy tales has captivated millions for over a century with the dream of never growing up, then in Australia, there exists another Peter Pan. One created solely to consume its own kind. Australia is no stranger to ecological mistakes. But this time, in an attempt to repair a disaster that has unfolded over nearly a century, science chose a path never taken before. Researchers deliberately engineered organisms designed to consume and eliminate up to 99% of their own species' eggs. In controlled experiments, the results were overwhelmingly positive. Yet for one critical reason, the project was never allowed to move beyond the laboratory. And now we're going to find out why. At the beginning of the 20th century, sugarcane was the economic backbone of Queensland. The industry accounted for more than 20% of the region's total agricultural value and supported tens of thousands of farming households. But just as the sugar industry reached its peak, a quiet crisis began to unfold. Gray sugarcane beetles spread rapidly across the fields, destroying root systems and causing sugar yields in some areas to fall by 30 to 40%. In desperation, Australia searched for solutions abroad. That search led them to reports from Puerto Rico describing a species of toad believed to feed on the larvae of agricultural pests. In 1932, researchers from the Bureau of Sugar Experiment Stations reached out for advice. But what they failed to do, a mistake that would prove fatal, was verify the claims. There were no laboratory tests, no field trials, no scientific confirmation that cane toads actually consumed the target pests. Every decision was based on second-hand reports from overseas. By 1935, approximately 102 South American cane toads were imported from Hawaii, bred, and released around Gordon in Queensland. Every cane toad in Australia today is believed to descend from this single, small founding population. At the time, no one believed that a few dozen toads could cause significant harm. But within just 70 years, they had become one of the most severe ecological disasters in Australia's history. Cane toads consume nearly everything in their path, from small animals to vegetation. Over time, they displaced native species across vast areas, transforming nearly 1.3 million square kilometers of Australia into territory dominated by an estimated 200 million cane toads. While Australia's human population in 2026 stands at roughly 27 million, cane toads outnumber people many times over, and nearly 20 times the total number of koalas remaining worldwide. And this is not a harmless backyard amphibian. Even in their native range in South America, cane toads are among the most toxic amphibians on Earth. Native predators there have spent millions of years evolving ways to avoid them or tolerate their toxins. Australia had no such evolutionary advantage. The body of a cane toad is, in effect, a living reservoir of poison. Two large glands behind its head secrete bufotoxin, a potent cocktail of cardiac toxins, neurotoxins, and compounds that disrupt vascular function. If a dog merely licks the milky white secretion, it can suffer seizures and die in under an hour. Worse still, bufotoxin is present at every stage of the cane toad's life cycle: eggs, tadpoles, juveniles, and adults. Fish that eat the eggs die. Small fish that consume tadpoles die. Goannas, or snakes that attempt to eat adult toads, almost certainly die. In an ecosystem like this, which predators can survive? Even the brown snake, one of the most venomous snakes in the world, can die within 2 to 30 minutes after ingesting a cane toad. Freshwater crocodiles, apex predators across many northern river systems, began dying en masse as cane toads spread. A 2008 study found that 77% of freshwater crocodiles died within 3 years, shortly after cane toads advanced inland from the Victoria River estuary. The rate of crocodile mortality matched the rate of cane toad invasion almost exactly. Goannas were among the hardest hit. In many regions, their populations declined by as much as 90% following the arrival of cane toads. Meanwhile, the toads themselves possess a reproductive strategy that is nearly impossible to contain. An adult female can lay between 20,000 and 30,000 eggs in a single breeding event, and under favorable conditions she can reproduce twice a year. That translates into billions of cane toad eggs produced annually. Their tadpoles are toxic as well. While less potent than adults, the toxin is still strong enough to kill small fish or native frogs that attempt to consume them. Notably, many predatory birds do not die from the toxin at this stage. Remember that detail. It will later become the foundation for the Peter Pan idea. Humans are not immune either. Direct contact can cause skin irritation, eye inflammation, and mild neurological symptoms. In northern Australia, cane toad poisoning is a common veterinary emergency. If you ever encounter one, avoiding contact is essential. The economic consequences have been just as severe. Australia's national science agencies estimate that the total ecological and indirect damage caused by cane toads has exceeded $2 billion. This figure includes the cost of biodiversity restoration, losses to ecotourism, and risks to the mining sector, an industry valued at approximately $136 billion. But there is a lesser-known detail. Cane toads in Australia are more toxic than their original populations. A 2015 study found that Australian cane toads have larger poison glands and bufadinolide concentrations 40 to 50% higher than those found in South American populations. And that is not even the worst part, because they are still becoming more dangerous. Between 2018 and 2022, multiple studies documented that cane toads are evolving at rates 5 to 10 times faster than typical wild vertebrates. In invasion-front populations, their bodies have changed in measurable ways. Legs approximately 6% longer, stronger musculature, enlarged livers, and lower baseline stress hormone levels. These changes allow them to travel farther, endure fatigue more effectively, and spread more rapidly. In the 1940s, a typical cane toad advanced roughly 8 kilometers per year. By the 2010s, that figure had increased to 40 to 60 kilometers annually, with the fastest individuals recorded at 76 kilometers per year, a rate faster than the width expansion of a small nation's border. A single mistake in 1935 did not simply persist. Over 80 years, it upgraded itself into a super-invasive variant. Worse still, the toads are not the only species changing. Other animals have begun altering their behavior and physiology in response. Goannas have abandoned hunting large prey and shifted toward insect-based diets. Some native mammals have even evolved smaller head sizes over time, reducing the risk of swallowing an adult cane toad whole. As of today, the number of cane toads in Australia is estimated to rival the entire population of Brazil. And every one of them is toxic and reproducing at an extreme rate. As a species, we have been playing God, whether we like it or not. The question is not whether we intervene, but whether we do so carefully, deliberately, and with enough understanding to repair at least some of the damage we have caused. That is why the research team led by Professor Rick Shine chose a radically different line of thinking. If adult cane toads could not be stopped, then intervention had to begin earlier, at the tadpole stage. At this point in their life cycle, cane toads are weaker, more concentrated, and far easier to control. From this logic, the Peter Pan concept emerged: to create tadpoles that never undergo metamorphosis, live 4 to 5 times longer than normal, and have enough time to consume nearly all the eggs of their own species. It sounds unrealistic, and in many ways, it is. That is precisely why the technical process is so complex. Each individual egg must be injected with CRISPR technology to disable the gene responsible for producing the hormone that triggers metamorphosis. To produce even a few thousand individuals, every egg has to be injected by hand. Biologically, the mechanism itself is straightforward. Tadpoles only metamorphose when their bodies produce sufficient thyroid hormone, a biological upgrade switch that initiates limb growth, tail reabsorption, and the transition to land. The research team uses CRISPR-Cas9 to turn that switch off. No hormone, no metamorphosis. The organism remains a tadpole for its entire life, much like Peter Pan himself. Each embryo, between 4 and 8 hours old, must be injected individually in experimental batches. The success rate is roughly 60 to 70%, which explains why scaling the process to population-level deployment remains a major challenge. In return, Peter Pan tadpoles grow larger, swim more powerfully, and consume roughly 3 times more eggs than normal tadpoles. But remember this detail: cane-toed tadpoles in Australia are already about 2.4 times more aggressive than their South American counterparts. That means even before any genetic modification, they are exceptionally effective egg predators. After genetic editing, they become a highly optimized version of that trait, specialists designed to consume their own species' eggs. When experimental data from 2023 to 2024 was compiled, researchers realized that Peter Pan was not merely different from ordinary tadpoles. It fundamentally collapsed the reproductive logic of cane toads. In the wild, normal cane-toed tadpoles remain in ponds for only 18 to 22 days before metamorphosing and leaving the water. Peter Pan tadpoles never make that transition. They live for 70 to 95 days, with the longest recorded individual surviving 98 days. The critical factor lies in the number of eggs consumed. A normal tadpole eats approximately 3,000 to 5,000 eggs before metamorphosis. A single Peter Pan individual consumes between 20,000 and 35,000 eggs before it dies, equivalent to an entire cane-toad egg clutch. In other words, just one Peter Pan tadpole is enough to completely eliminate a single reproductive event. The factor that most concerns ecosystem managers is the risk of spread, and here, the number is effectively 0. Peter Pan cannot metamorphose, cannot leave the water, and cannot reproduce. It remains trapped in a pond, existing solely to consume eggs before completing its life cycle. There is no next generation, no migration, and no risk of creating a new invasive species. And yet, precisely because the numbers are so impressive, it is easy to overlook the remaining risk. That overlooked risk is the reason this project has never been deployed outside controlled conditions. First, one decisive point must be made clear. The gene-edited tadpoles created under the Peter Pan project do not consume only cane-toad eggs. In controlled experiments, researchers observed that they also consumed the eggs of some native frog species, albeit at very low rates. The impact was not enough to collapse native populations or cause widespread decline. But in ecology, the critical boundary is not between large and small, but between 0 and not 0. That single fact alone was enough to halt every proposal to release Peter Pan into the natural environment. This was not excessive caution, but a direct response to the ecological lessons Australia has already paid for in the past. Before advancing to Peter Pan, the research team conducted simpler gene editing experiments to assess unintended risks. One of the earliest involved disabling the gene responsible for skin pigmentation, creating albino cane toads. Technically, CRISPR performed exactly as intended. Biologically, however, the albino individuals died at significantly higher rates, even under laboratory conditions. More importantly, albino toads showed a tendency to undergo premature metamorphosis under stress. A single gene edit had triggered a cascade of unforeseen physiological changes. At that point, the core question shifted. It was no longer whether humans had edited the correct gene, but whether we truly understood the biological systems we were intervening in. And unlike in 1935, Australian science chose to move slowly this time. As of early 2026, all trials remain confined to closed systems. Not because the solution is ineffective, but because in ecology, a small risk that cannot be reversed will always outweigh a benefit that is nearly perfect. Which approach do you think is the right one? And should Peter Pan ever be tested in the open environment?